Hello and welcome. Does the wave equation make sense? Well, let's see. Here we have some piece of string, and we have u as the vertical position and x as the horizontal position. U is a function of x and t, with x being the horizontal position and t being time. Now we have that the second derivative of u with respect to t is the vertical acceleration at a point, like say this point. And the second derivative of u with respect to x is the concavity at that point. So what this equation is saying is that the acceleration at the point equals the concavity at the point. So for example, if we had a concavity of +5 at this point, then our vertical acceleration at this point should be +5. Now, why would that be? Well, along this string, there is tension, and we have some tension going like that and some tension going like that. Now, the horizontal components of the tension are going to cancel out. That is, the string isn't moving side to side anywhere, but the vertical components of the tension are going to combine together to give us a positive upwards force. Well, a positive force in the upwards direction would give us a positive acceleration in the upwards direction because of F equals ma. Now let's see what happens if we add a friction term to the equation. So the first derivative of u with respect to t is the velocity, the vertical velocity at the point. So we can imagine that we're in some kind of fluid, so when we move through the fluid, the faster we move through the fluid, the more resistance we have towards movement in that direction. Now, we're saying that these two have to add together to give us the concavity. So let's say if the concavity is 10, then these need to add to 10. Well, what that means is it's sort of like a seesaw effect, right? If ut gets bigger, then utt has to get lesser. So it's like this, right? So I like to say that the friction term absorbs from the acceleration term. So that is, as the friction term increases, that is, as our vertical velocity increases and we're getting resistance, our acceleration term, we're absorbing from the acceleration term, which has to get smaller, lesser and lesser. So for example, we might have, if the velocity is 5, then the acceleration would have to be 5. But in the same situation, if the velocity went up to 7, that is 2 greater, then our acceleration would have to go down to 3, that is 2 lesser. So we absorbed 2 extra units by going from 5 to 7. And then here is the general form of the wave equation, but this time it's two-dimensional. We have the x dimension and the y dimension. So if you're like looking down on a plane, it might be like waves above the plane, right? So what this is saying is that the acceleration at a point, how do we get that? Well, we just add the concavity along the x dimension to the concavity along the y dimension. And here I finally introduced a constant, and of course there should be constants throughout all of this. I should have a positive constant here and a positive constant here. These are sort of like the exchange rates, right? It's like, is one concavity worth 1 acceleration, or is one concavity worth 2 acceleration, or is it worth half an acceleration? C-squared determines that exchange rate. Now let's look at one more example here, which is if we had a negative concavity in the x direction, let's say -5, and then we have a positive concavity along the y direction, let's say +5. So our concavity in the x direction and our concavity in the y direction, those two are canceling out. And if you looked at that point, it's sort of like the saddle shape, right? You have a saddle point there where you're kind of going like, you're going like this in this direction and like this in this direction, and it perfectly cancels out. So the acceleration there is actually going to be 0, which is really intuitive and nice to think about, that point isn't accelerating, but the points surrounding it are accelerating. Some of them are kind of coming up to catch up, and the ones over here are kind of going down. or not going down and going up, but accelerating up and going and accelerating down. I think I got that reversed, but I think you get what I mean, right? This point might be going up or it might be going down. We're just saying which direction it's accelerating in. Thank you for taking a look at this video. I hope it was interesting. Goodbye.